Hello friends, today I am going to discuss about high level data link control protocol, that is HDLC protocol. It is a most important data link layer protocol. To satisfy a variety of applications, HDLC defines three types of stations, two link configurations and three data transfer modes of operation. The three stations are primary station, secondary station and combined station. Primary station is responsible for controlling the operation of the link. Frames issued by the primary station are called as commands. Secondary stations operates under the control of primary stations. Frames issued by the secondary stations are called as responses. The primary station maintains a separate logical link with each secondary station on the line. Combined station combines the features of primary and secondary stations. Any combined station can able to issue both commands as well as responses. Then link configurations. There are two link configurations, unbalanced configuration and balanced configuration. Unbalanced configuration consists of one primary and one or more secondary stations and support both full duplex and half duplex transmission modes. Balanced configuration consists of two combined stations and supports both half duplex and full duplex transmission modes. Then HDLC transfer modes. There are three data transfer modes: normal response mode, asynchronous balanced mode, and asynchronous response mode. Normal response mode is used with an unbalanced configuration. The primary may initiate data transfer to the secondary, but secondary may only transmit data in response to the command from the primary. Then asynchronous balanced mode. It is used with a balanced configuration. Any combined station may initialize transmission without receiving permission from the other combined station. Then asynchronous response mode. It is used with an unbalanced configuration. The secondary may initiate the transmission without explicit permission of the primary. But here the primary still retains responsibility for the line, including initialization, error recovery, and logical disconnection. Normal response mode is used on multi-drop lines in which a number of terminals are connected to a host computer. The computer ports each terminal for input. Normal response mode is also sometimes used on point-to-point links, particularly if the link connects a terminal or other peripheral to a computer. Asynchronous balance mode is most widely used of the three modes. It makes more efficient use of full duplex point-to-point link because there is no pooling overhead. ARM mode is rarely used. It is applicable to some special situations in which the secondary station may need to initiate transmission. Then frame structure. Figure shows the frame structure of HDLC frame. It uses HDLC protocols uses the synchronous transmission. All transmissions are in the form of frames. The single frame format for all data and control exchanges is used in the HDLC protocol. The flags. Our first flag, address and control field, preceding to the information field are known as the header, and the fields, that the FCS flag field at the last, that is the after information field, are referred as a trailer. Then we will see flag fields. The flag fields delimit the frame at both ends with a unique pattern 0, 6 continuous 1 and 0. A single frame may be used as a closing flag for one frame and opening flag for the next frame. On both sides of the user network interface, receivers are continuously hunting for the flag sequence to synchronize on the start of the frame. While receiving a frame, the station continues to hunt for the sequence to determine the end of the frame. Because the protocol allows the presence of arbitrary bit patterns, there is no assurance that the bit pattern 0, 6 continuous ones, and 0 will not appear somewhere inside the frame, thus destroying synchronization. To avoid this problem, a procedure known as bit stepping is used. For all bits between the starting and ending flag, the transmitter inserts an extra 0 bit after each occurrence of continuous ones in the frame. After detecting a starting flag, the receiver monitors the bit stream. When a pattern of 5 ones appears, the sixth bit is examined. If this bit is 0, it is deleted. If the sixth bit is 1 and the seventh bit is 0, the combination is accepted as a flag. If the sixth bit and seventh bit are both 1, the sender is indicating an abort condition. With the use of bit stepping, arbitrary bit patterns can be inserted into a data field of the frame. This property is known as a data transparency. Figure shows example of the bit stepping. Then address field. The address field identifies the secondary station that has transmitted or is to receive the frame. This field is not needed for point-to-point links but is always included for the sake of uniformity. The address field is usually 8 bits long, but by prior agreement, an extended format may be used in which the actual address length is multiple of 7 bits. The leftmost bit of each octet is 1 or 0 according as it is or it is not the last octet of the address field. The remaining 7 bits of each octet form a part of the address. The single octet addresses of all ones is interpreted as a all stations address in both basic and extended frames, that is the broadcast address. It is used to allow the primary to broadcast a frame for reception by all secondaries. Then control field. HDFC defines 3 types of frames. That is, information frames carry the data to be transmitted for the user. Additionally, flow and error control data using the ARQ mechanism are piggybacked on the information frame. Supervisory frames provide a ARQ mechanism when piggybacking is not used. Unnumbered frames provide a supplemental link control functions. The first or the 2 bits of the control field serves to identify the frame type. The remaining bit positions are organized into subfields as indicated in the figure. Then all the control frames formats contain a pole final bit. Its use depends on context. Typically, in command frames, it is referred as a P bit, that is the pole bit. And in response frames, it is referred as a final bit. In response frames, this bit is set to 1, and in command frames, this P bit is also set to 1. Then, the basic control field for S frames, I frames uses the 3-bit sequence numbers. With the appropriate set mode command, the extended control field can be used for this S and I frames that employs 7-bit sequence numbers. Q frames always contains 8-bit control field. Then information field. The information field is present only in I frames and some U frames. The field can contain any sequence of bits but must consist of an integral number of octets. The length of the information field is variable up to some system-defined maximum value. Then FCS field, that is field check sequence field. Frame check sequence field is an error detecting code calculated, or it contains the error detecting code calculated from the remaining bits of the frame. Then it may be uses 16-bit CRC estimations or 32-bit CRC estimations. Next is HDLC operation. The HDLC operation consists of exchange of I frames, S frames and U frames between the two stations. The operation of HDLC involves three phases. The first page is initialization page, second one is data transfer page, and third one is disconnect page. Then we will see one by one these pages. Initialization page. Either side may request initialization by issuing one of the 6 set mode commands. Then this command serves three purposes. It signals the other side that initialization is requested. It specifies which of the three modes, that is NRM, ABM or ARM, is requested. It also specifies whether 3 or 7-bit sequence number are to be used. If the other side accepts this request, then the HDLC module on the other end transmits a unnumbered acknowledgement, that is UA frame. If the request is rejected, then it transmits the disconnected mode frame to the sender, that is DM frame. Then next page is the data transfer page. When the initialization has been requested and accepted, then a logical connection is established. Both sides may begin to send user data in iframes starting with specific number 0. The NS and NR fields of the iframe are sequence number that support the flow control and error control mechanisms. An HDLC module sending a sequence of iframes will number them sequentially modulo 8 or modulo 128 depending upon whether 3 or 7-bit sequence numbers are used. So here NS represents the send sequence number and NR represents the acknowledgement for iframes received. It enables the HDLC module to indicate which number iframe is expects to receive next. S frame are also used for flow control and error control. The receive ready frame, that is RR frame, acknowledges the last iframe received by indicating the next iframe expected. The RR is used when there is no reverse user data traffic to carry an acknowledgement. RNR, that is receive not ready, acknowledges an iframe as with RR, but also asks the peer entity to suspend the transmission of iframes. When the entity that issued RNR is again ready, it sends an RR frame. Then reject frame, that is REJ, initiates the go back in ARQ mechanism. It indicates that the last iframe received has been rejected and the retransmission of all iframes beginning with the number NR is required. Selective reject, that is SREJ, is used to request retransmission of just a single frame, that is the errors frame. Then next page is disconnect page. In either, that is any HDLC module can initiate a disconnect, either on its own initiative if there is some sort of fault or at the request of its higher layer user. HDLC issues a disconnect by sending a disconnect frame, that is DISC frame. The remote entity must accept the disconnect by replying with the UA, unnumbered acknowledgement, and informing its layer 3 that the connection has been terminated. Any outstanding unacknowledged iframe may be lost and their recovery is the responsibility of the higher layers. Then examples of the operation. To better understand HDLC operations, several examples are presented in this figure. In the example diagrams, each arrow indicates a legend that specifies the frame name, the setting of the pole final bit, and where appropriate the values of NR and NS. The setting of P or F bit is 1 if a destination is present, and it is set to 0 if destination is absent. Figure A shows the frames involved in link setup and disconnect. The HDLC protocol entity for one side issues an SABM command to the other side and starts a timer. The other side, upon receiving the SABM, returns a UA response and sets local variable and counters to their initial values. The initiating entity receives the UA response, sets its variable and counters and stops the timer. The logical connection is now active and both sides may begin transmitting frames. The timer expiry without a response to the SABM, the originator will repeat the SABM as illustrated in the figure. This would be repeated until UA or DM is received or until after a given number of tries. The entity attempting initiation gives up and reports failure to the management entity. In such a case, higher layer intervention is necessary. The same figure, that is figure A, shows the disconnect procedure. On other issues, the disc command or here, if disconnection is expected, the other side station issues the disconnect command and the next side responds with the UA response, which is shown here. That is, A sends the disconnect command and B responds with the OK. The sum figure, that is figure A, shows the disconnect procedure. One side issues a disc command and the other responds with UA response. The figure B illustrates the full duplex exchange of iframes. When an entity sends a number of iframes in a row with no incoming data, then the receiver sequence number is simply repeated. When the entity receives a number of iframes in the row with no outgoing frames, then the receiver's sequence number is the next outgoing frame must reflect the cumulative activity. Note that the addition of iframes data exchange may involve supervisory frames. Then figure C shows an operation involving a busy condition. Such a condition may arise between an HDLC entity is not able to process iframes as fast as they are arriving, or the intended user is not able to accept data as fast as they arrive in iframes. In either case, the entity's receiver buffer fills up and it must halt the incoming flow of iframes using an RNR command. In this example, the A issues an RNR which requires B to halt transmission of iframes. The station receiving the RNR will usually poll the busy station at some periodic interval by sending the RR with the P bit set. This requires the other side to respond with either an RR or RNR. When a busy condition has cleared, A returns an RR and iframe transmission from B can resume. An example of error recovery using the reject command is shown in the figure D. In this example, A transmits iframes numbered 3, 4 and 5. Number 4 suffers an error and is lost. When B receives iframe number 5, it discards this frame because it is out of order and sends and reject with an NR of 4. This causes station A to initiate retransmission of iframes previously sent, beginning with frame number 4. Station A may continue to send additional frames after the retransmitted frames. An example of error recovery using a timeout is shown in the figure E. In this example, station A transmits iframe number 3 as the last in a sequence of iframes. The frame suffers an error. Then station B detects the error and discards it. However, station B cannot send and reject because there is no way to know if this was an iframe. If an error is detected in an frame, all of the bits of that frame are suspect and the receiver has no way to act upon it. Station A, however, would have started a timer as the frame was transmitted. This timer has duration long enough to span the expected response time. When the timer expires, station A initiates a recovery action. This is usually done by pulling the other side with an RR command with the P bit set. This is to determine the status of the other side. Because the pull demands a response, the entity will receive a frame containing a NR field and be able to proceed. In this case, the response indicates that frame 3 was lost, which station A retransmits. These are the few examples of operation. Then other DLC protocols. Other examples of the data link control protocols are LabD, which are derived from the basic HDLC protocol, or HDLC protocol is modified, or these are the sub protocols of the HDLC protocol. So here LabD is the link access procedure balanced channel. This is a part of X.25 protocol or functionality. It is a subset of HDLC asynchronous, which uses the asynchronous balanced mode of operation. It is used on point-to-point links between system and packet switching network node. The next is the LabD protocol, that is the link access procedure for D channel, and it is most widely used in ISDS networks. It utilizes the asynchronous balanced mode of operation, and it always uses the 7-bit sequence number, no 3-bit sequence number, and 16-bit address field contains 2 sub-addresses, one for device and one for user. This is about HDLC protocol. Thank you.